and welcome to another journey through the cosmos. Tonight, we'll explore our home in the universe, the Milky Way galaxy, a vast island of stars, gas, and dust spinning slowly through the darkness of space. As we drift through these facts together, let your breathing slow, your thoughts settle, and allow the gentle rhythm of discovery to carry you into rest. The universe is patient, and so shall we be. Let's begin. The Milky Way galaxy is not just a distant object we observe through telescopes. It is our home, the cosmic neighborhood where Earth resides. Every star you've ever seen with your naked eye, every constellation that has guided travelers throughout history, exists within its boundaries. We are embedded deep within its structure, approximately 2/3 of the way from its bright central core to its faint outer edge. From our vantage point inside, the galaxy appears as a luminous band stretching across the night sky, a river of light that ancient cultures saw as milk spilled across the heavens. This is where our story begins, inside the only galaxy we can study from within. Within the Milky Way's vast expanse shine between 100 billion and 400 billion stars. The exact number remains uncertain because many are too dim or too distant for even our most powerful telescopes to detect individually. Each of these stars burns with its own particular light, ranging from massive blue giants radiating fierce energy to tiny red dwarfs that will glow gently for trillions of years. Some are newborns, just beginning their long stellar lives. Others are ancient, formed when the universe itself was still young. Together, they create the soft glow we observe from Earth, a collective brilliance that speaks of countless individual flames scattered across unimaginable distances. To grasp the scale of our galaxy, imagine light traveling at its maximum speed through empty space. In 1 year, that light covers nearly 6 trillion miles. The Milky Way's stellar disk stretches approximately 100,000 of these light years from edge to edge. This measurement represents not just distance, but time itself. For when we observe the opposite side of the galaxy, we see it as it appeared 100,000 years ago. The light departing from stars on the far rim began its journey when early humans were still learning to control fire. Space and time intertwine across these cosmic distances, reminding us that to look outward is also to look backward through history. The solar system occupies a position roughly 2/3 of the way from the Milky Way's core to its outer boundary. More precisely, we orbit at a distance of about 27,000 light-years from the central supermassive black hole that marks the galaxy's gravitational heart. This placement in the galactic suburbs may prove fortunate for life. Some astronomers suggest that closer to the center, intense radiation and frequent stellar encounters might have disrupted Earth's stable orbit. Farther out, the scarcity of heavy elements needed for rocky planets would make worlds like ours less common. We inhabit a region sometimes called the Galactic Habitable Zone, though whether such a zone truly exists remains a subject of ongoing research and debate. When viewed from above or below, the Milky Way reveals an elegant spiral structure with a distinctive bar of stars cutting across its central region. two major spiral arms, named Perseus and Scutum Centaurus, sweep outward from the ends of this bar, forming graceful curves that wrap around the galactic core. Between these dominant arms lie smaller structures, including the Orion Spur, where our solar system resides. This barred spiral design is common among galaxies in the universe, though each displays unique variations in the strength of its bar and the tightness of its spiral arms. The bar itself consists of older stars moving in elongated orbits, their collective motion helping to channel gas toward the galactic center, where it can fuel new star formation. Our solar system makes its home within the Orion Arm, also known as the Orion Spur or local arm. This structure is not one of the galaxy's major spiral arms, but rather a minor arm or bridge of stars, spanning approximately 3,500 light-years in width and 20,000 light-years in length. It connects the larger Perseus and Sagittarius arms, forming a partial spiral of its own. The Orion Arm contains many familiar celestial landmarks visible from Earth, including the Orion Nebula, Betelgeuse, Rigel, and the stars of Orion's belt. When we gaze at these bright objects in our night sky, we are looking along our own local spiral arm, seeing neighbors that share our galactic neighborhood. The Milky Way galaxy formed during the universe's early youth, roughly 13.6 billion years ago. This age has been determined through studies of the oldest stars found in globular clusters, dense spherical collections of ancient suns that orbit in the galaxy's halo. These venerable stars contain very few heavy elements, marking them as members of the first stellar generations born after the Big Bang. By measuring their ages through observations of white dwarfs and detailed stellar evolution models, astronomers can look back to the epoch when our galaxy first began to take shape. The Milky Way is therefore nearly as old as the universe itself, which emerged from the Big Bang approximately 13.8 billion years ago. At the very heart of the Milky Way lies Sagittarius, a star, a supermassive black hole with a mass equivalent to roughly 4.3 million suns. Despite this enormous mass, the black hole itself is surprisingly compact, with an event horizon measuring only about 14.6 million miles across, roughly the size of Mercury's orbit around our Sun. Astronomers discovered this hidden giant by observing stars that orbit incredibly close to the galactic center, their velocities reaching thousands of miles per second as they whip around an invisible gravitational anchor. These observations earned scientists the 2020 Nobel Prize in Physics. The black hole sits approximately 26,000 light-years from Earth in the direction of the constellation Sagittarius. Unlike a solid wheel that rotates as one piece, the Milky Way exhibits differential rotation. Stars closer to the galactic center complete their orbits much faster than those farther out, following the same principles that govern planetary motion around the Sun. This differential rotation means that our position in space, relative to the galactic core, changes slowly over time. The spiral arms themselves are not fixed structures of stars, but rather waves of density that move through the stellar disk, triggering star formation as they compress into stellar gas. Stars drift in and out of these arms throughout their lifetimes, much as cars might move through waves of traffic on a highway. The Sun, along with Earth and the other planets, travels through space at approximately 500,000 miles per hour relative to the galactic center. Despite this tremendous velocity, the vast distances involved mean that completing one full orbit takes roughly 230 million years. Astronomers sometimes refer to this period as a cosmic year or galactic year, since the Sun formed about 4.6 billion years ago. It has completed approximately 20 orbits around the Milky Way. The last time we occupied our current position in the galaxy, dinosaurs were beginning their long reign on Earth. The next time we return here, Earth will be a vastly different world, if it still exists at all. Everything we can see in the Milky Way accounts for only a small fraction of its total mass. The rest consists of dark matter, a mysterious substance that neither emits nor absorbs light. We know dark matter exists because of its gravitational effects. Stars in the outer regions of the galaxy orbit much faster than they should based on the visible matter alone. Without an enormous halo of dark matter surrounding and permeating the galaxy, these outer stars would fly off into intergalactic space. Current estimates suggest that dark matter outweighs visible matter by a factor of 10 to 1 or more, making up perhaps 90% of the galaxy's total mass. The nature of dark matter remains one of astronomy's greatest unsolved mysteries. While the luminous disk of the Milky Way stretches about 100,000 light-years across, the dark matter halo extends much farther, perhaps encompassing a region 300,000 to 400,000 light-years in radius. This invisible cocoon of dark matter provided the gravitational framework within which the visible galaxy formed. In the early universe, dark matter collapsed first, creating potential wells into which ordinary matter could fall and coalesce into stars and gas clouds. Even today, this dark halo continues to shape the galaxy's structure and motion, acting as a gravitational scaffold that holds everything together. Recent observations suggest the dark matter halo may be tilted or elongated rather than perfectly spherical, adding complexity to our understanding of galactic structure. The Milky Way's stellar disk actually consists of two components with different characteristics. The thin disk, only about 1,000 light-years thick at the Sun's location, contains the youngest stars, most of the gas and dust, and virtually all active star formation. This is where spiral arms are most prominent, and where new stellar nurseries continually light up. The thick disk, extending several thousand light-years above and below the thin disk, contains older stars that formed earlier in the galaxy's history. These populations have different orbital velocities and chemical compositions, telling a story of the galaxy's evolution from a more chaotic early state to its current organized structure. Rising above and below the flat disk near the galaxy's center is a bulge of stars, a roughly spherical concentration measuring about 10,000 light-years in diameter. This bulge glows with the soft golden light of billions of old stars, most of them ancient red giants that formed in the galaxy's early epochs. Star formation has largely ceased in the bulge, as most of the gas there has already been converted into stars or blown away by stellar winds and supernova explosions. The stars in the bulge move in complex orbits, creating a three-dimensional structure quite different from the orderly rotation of the disk. At the very center of this bulge lies the supermassive black hole, Sagittarius, a star, hidden from direct view by thick clouds of dust. Between Earth and the galactic core stretch vast clouds of interstellar dust, tiny particles of carbon, silicon, and other elements expelled from dying stars. These microscopic grains block visible light, making it impossible to see the galaxy's central regions using ordinary optical telescopes. The view towards Sagittarius reveals dark lanes cutting through the Milky Way's bright band, silhouettes of dense molecular clouds. To peer through this obscuring material, astronomers must use longer wavelengths. Infrared light, radio waves, and X-rays can penetrate the dust, revealing the hidden activity in the galactic center. These observations have unveiled a dynamic region filled with rapidly orbiting stars, glowing gas clouds, and the gravitational influence of the supermassive black hole. Orbiting in the galactic halo are approximately 150 globular clusters, dense spherical collections of stars that date from the galaxy's earliest epochs. Each cluster contains hundreds of thousands to millions of stars packed into regions only a few dozen light-years across. Within a globular cluster, stars are separated by distances measured in light weeks rather than light years, creating a celestial environment utterly unlike our own sparse neighborhood. These clusters are among the oldest objects in the Milky Way, with ages approaching 13 billion years. They formed before the galaxy had settled into its current disk shape, and they still follow orbits that carry them high above and far below the galactic plane, tracing the galaxy's original spherical form. The stars within globular clusters are population 2 objects, ancient suns that formed when the universe contained very few elements heavier than hydrogen and helium. By studying these stars, astronomers can measure the age of the galaxy itself and trace its chemical evolution over billions of years. The oldest globular clusters appear to have formed within just a few 100 million years after the Big Bang, making their stars nearly as old as the universe. Some clusters show signs of multiple stellar populations, suggesting complex formation histories that challenge simple models of how these systems assembled. The study of globular clusters provides a window into conditions that existed during the Milky Way's infancy. Surrounding the disk and bulge is a vast spherical halo, a diffuse region containing individual stars and globular clusters scattered throughout an enormous volume. This halo extends at least 100,000 light-years from the galactic center, perhaps much farther. The stars in the halo are generally old and metal-poor, moving on highly elliptical orbits that carry them through the disk and out into the distant reaches of intergalactic space. Some of these stars may have formed in the Milky Way's original gas cloud, while others are likely refugees from smaller galaxies that merged with our own in the distant past. The halo is a fossil record of the galaxy's assembly history, preserving memories of ancient collisions and accretion events. Rather than lying perfectly flat, the Milky Way's disk is warped, with one edge bent upward and the other downward relative to the central plane. This distortion becomes more pronounced toward the galaxy's outer regions, creating a shape reminiscent of a warped vinyl record or a sombrero's brim. The warp may result from gravitational interactions with satellite galaxies, particularly the Large and Small Magellanic Clouds, which orbit the Milky Way and exert tidal forces through the dark matter halo. As these smaller galaxies move, they create ripples in the dark matter, which in turn affects the distribution of gas and stars in the outer disk. The warp reveals that galaxies are not static structures, but dynamic systems constantly being reshaped by gravitational forces. Despite its age, the Milky Way remains an active star-forming galaxy, creating new stars at a rate of approximately 1 to 3 solar masses per year. This ongoing birth of stars occurs primarily in the spiral arms, where giant molecular clouds collapse under their own gravity. Within these dense clouds, thousands of stars can form together in clusters, lighting up their surroundings with intense ultraviolet radiation. The Orion Nebula, visible to the naked eye as a fuzzy patch in the Sword of Orion, is one of the nearest active star-forming regions, located about 1,300 light-years from Earth. These stellar nurseries ensure that the galaxy continues to evolve, with each new generation of stars enriching the interstellar medium with heavy elements created through nuclear fusion. The coldest and densest regions of the Milky Way are giant molecular clouds. Vast accumulations of hydrogen gas mixed with dust and trace amounts of other molecules. These clouds can span hundreds of light years and contain the mass of millions of suns. Within their frigid interiors, where temperatures hover just a few degrees above absolute zero, gravity slowly pulls material together. When a region becomes dense enough, it collapses, heating up until nuclear fusion ignites in its core, and a new star is born. The process is neither gentle nor efficient. Stellar winds and supernova explosions from the first massive stars to form can blast away much of the remaining gas, halting further star formation and dispersing the cloud. What remains is an open cluster of young stars, slowly drifting apart over millions of years. Hydrogen is by far the most abundant element in the Milky Way, as it is throughout the universe. Most of this hydrogen exists in diffuse form, spread thinly through the space between stars. Radio telescopes can detect neutral hydrogen through the radiation it emits, at a wavelength of 21 centimeters, allowing astronomers to map the distribution of gas throughout the galaxy. These observations reveal that hydrogen gas traces out the spiral arm structure more clearly than visible stars do, because the gas is less affected by obscuring dust. The largest concentrations of hydrogen are found in the outer regions of the disk, forming a reserve of raw material for future generations of stars. Understanding the distribution and motion of hydrogen gas is crucial for comprehending the galaxy's dynamics and evolution. The Milky Way did not form in isolation, but grew through the accumulation of smaller galaxies over billions of years. Evidence of this violent past appears in stellar streams, long ribbons of stars stretched across the sky that mark the remains of dwarf galaxies torn apart by tidal forces. The stellar halo itself is believed to contain many such remnants, each stream telling the story of a long-ago merger. Some globular clusters may be the surviving cores of dwarf galaxies, stripped of their outer layers but still holding together as bound systems. This process of galactic cannibalism continues today. Several small galaxies currently orbit the Milky Way, and some are being pulled apart right now, their stars slowly joining our galaxy's halo. One of the closest satellite galaxies to Earth, the Sagittarius Dwarf elliptical galaxy, is currently being torn apart by the Milky Way's gravitational field. This small galaxy passed through the Milky Way's disk several times during the past few billion years, and each passage stripped away more of its stars. Today, long streams of stars from this disrupted galaxy wrap around the Milky Way several times, creating a faint stellar structure visible to sensitive surveys. The eventual fate of these stars is to become fully incorporated into the Milky Way's halo, their origin as members of a separate galaxy erased except in the subtle chemical signatures they carry. Watching this merger unfold in real time provides insights into how larger galaxies grow through the accretion of smaller ones. Visible from the southern hemisphere, the large Magellanic Cloud appears as a bright, irregular patch of light, a small companion galaxy orbiting our own. Located approximately 160,000 light-years from Earth, it contains roughly 30 billion stars and shows active star formation. The large Magellanic Cloud has been gravitationally bound to the Milky Way for billions of years, though recent measurements suggest it may be on its first passage rather than a stable orbit. If so, it will eventually merge with the Milky Way, adding its stars and gas to our galaxy. The supernova that occurred in the Large Magellanic Cloud in 1987 was the closest supernova to Earth in nearly 400 years, providing astronomers with an unprecedented opportunity to study these explosive stellar deaths up close. The small Magellanic Cloud, slightly farther away at about 200,000 light-years, is another satellite galaxy visible from southern latitudes. It contains approximately 3 billion stars and shows a more irregular structure than its larger neighbor. A bridge of gas and stars connects the two Magellanic Clouds, suggesting they may have interacted gravitationally in the past. Both clouds are being distorted by tidal forces from the Milky Way, with streams of gas trailing behind them as they orbit. These gas streams, known as the Magellanic Stream, were discovered through radio observations and span a huge arc across the sky. They provide evidence that the interaction between large and small galaxies involves not just stars, but also vast quantities of gas being exchanged or stripped away. Our galaxy is part of a small cluster called the Local Group, which contains approximately 80 known galaxies within a diameter of roughly 10 million light-years. Most of these are dwarf galaxies, small systems containing just millions or billions of stars. The Local Group is dominated by two large spiral galaxies, the Milky Way and the Andromeda Galaxy, with the Triangulum Galaxy being the third largest member. All these galaxies are gravitationally bound to each other, orbiting around their common center of mass. The Local Group represents our immediate cosmic neighborhood, a gravitationally connected family of galaxies that will eventually merge over billions of years, assuming the expansion of the universe doesn't pull them apart first. The Andromeda Galaxy, also known as Messier 31, lies approximately 2.5 million light-years from Earth. It's a magnificent spiral galaxy, larger than our own, containing roughly 1 trillion stars compared to our few 100 billion. On a clear, dark night, Andromeda is visible to the naked eye as a faint smudge of light in the constellation of the same name. What we see with our eyes is actually the galaxy's bright central bulge. Long exposure photographs reveal its full glory, showing spiral arms that span more than 6 times the width of the full moon in our sky. Andromeda has been known since ancient times, though people didn't recognize it as another galaxy until Edwin Hubble's observations in the 1920s proved that it lay far beyond the boundaries of the Milky Way. Despite the universe's overall expansion, the Milky Way and Andromeda are moving toward each other at about 250,000 miles per hour. Measurements of Andromeda's motion across the sky, made possible by the Hubble Space Telescope's precise observations, suggest that this approach will likely culminate in a collision approximately 4 to 4.5 billion years from now, though recent studies indicate there may be as much as a 50% chance the galaxies could miss each other entirely. If they do collide, the encounter will not be a catastrophic crash, but rather a slow gravitational ballet lasting billions of years. During multiple close passes, both galaxies will be gravitationally distorted, their spiral arms stretched into long tidal tails of stars. Star formation will surge as gas clouds collide and compress. Eventually, after several encounters, the two galaxies may merge into a single enormous elliptical galaxy, sometimes nicknamed Milkomeda or Milkdromeda. Despite the dramatic transformation awaiting our galaxy, the collision with Andromeda poses little direct threat to individual solar systems. The space between stars is so vast that even when two galaxies interpenetrate, the probability of any two stars actually colliding is vanishingly small. To understand this, consider that the nearest star to our Sun is over 4 light-years away. If the Sun were the size of a grain of sand, the next grain of sand would be over 4 miles distant. When the galaxies merge, most stars will simply pass by each other, their orbits altered by the changing gravitational field, but their physical integrity intact. The real action will occur in the gas clouds, which will collide and compress, triggering intense bursts of new star formation. By the time the Milky Way and Andromeda potentially collide, Earth will likely already be a barren world. The Sun is gradually growing brighter as it ages, and current models suggest that within about 1 to 1.5 billion years, this increased luminosity could heat Earth's surface enough to trigger a runaway greenhouse effect and end all life. During the galactic merger itself, roughly 4 billion years from now, computer simulations indicate there's approximately a 50% chance that our solar system will be flung from its current orbit to a location 3 times farther from the new galaxy's center. There's also about a 12% chance that the gravitational chaos will eject the solar system entirely into intergalactic space. Even if this happens, the solar system would remain gravitationally bound, with the planets continuing to orbit the Sun. The night sky would simply contain fewer stars, and the merged galaxy would appear as a distant collection of light. The final product of a potential Milky Way Andromeda collision would be a massive elliptical galaxy, a smooth spherical or football-shaped collection of stars, lacking the distinct spiral arms of its parent galaxies. This transformation occurs because the merger scrambles stellar orbits, destroying the organized rotation that maintains spiral structure. The new galaxy would contain over 1 trillion stars and spans several 100,000 light-years. At its center, the supermassive black holes from both the Milky Way and Andromeda would spiral together, eventually merging into an even more massive black hole. Based on our understanding of black hole physics, this merger would release tremendous energy in the form of gravitational waves, ripples in space-time that may be detectable by future space-based observatories, providing astronomers elsewhere in the universe with a signal of this cosmic event. While visible light cannot penetrate the dust clouds shrouding the galactic center, other forms of radiation reveal this hidden region's complexity. Infrared observations show millions of closely packed stars orbiting the central black hole. Radio telescopes detect the black hole itself as a compact, bright source known as Sagittarius, a star. X-ray observatories observe hot gas swirling toward the event horizon and occasional flares of high-energy radiation when material falls into the black hole. Gamma-ray telescopes have found mysterious emissions that might result from dark matter particles annihilating near the galactic core. Each wavelength provides a different view of this extreme environment, where gravity's pull is so strong that the laws of physics operate in their most extreme regimes. Some of the best evidence for the supermassive black hole comes from observing stars that orbit extremely close to it. One such star, designated S2, follows an elliptical path that brings it within just 17 light-hours of the black hole once every 16 years. At its closest approach, this star travels at nearly 3% of the speed of light, roughly 14 million miles per hour. By tracking the positions and velocities of these fast-moving stars over decades, astronomers have precisely measured the mass and location of the black hole. These observations also provide tests of Einstein's theory of general relativity in the strong gravitational field near a black hole. And so far, the theory has passed every test. In addition to the supermassive black hole at its center, the Milky Way harbors millions of smaller stellar mass black holes scattered throughout its disk and halo. These black holes form when massive stars, those with more than about 20 times the Sun's mass, exhaust their nuclear fuel and collapse catastrophically. The resulting black holes typically have masses between 3 and 50 times that of the Sun. Most float invisibly through space, detectable only if they happen to have a companion star from which they can steal material. As gas spirals into a stellar mass black hole, it heats to millions of degrees and emits intense X-rays, creating X-ray binary systems that astronomers can observe. Recent gravitational wave detections have revealed mergers of stellar mass black holes throughout the universe, including likely within our own galaxy. When stars with masses between about 8 and 20 solar masses reach the ends of their lives, they too explode as supernovae. However, rather than leaving behind a black hole, these explosions produce neutron stars, incredibly dense objects composed almost entirely of neutrons. A neutron star packs roughly 1.4 times the Sun's mass into a sphere only about 12 miles across. A teaspoonful of neutron star material would weigh about 1 billion tons on Earth. Some neutron stars rotate extremely rapidly, emitting beams of radio waves that sweep across space like lighthouse beacons. These are pulsars, and astronomers have discovered over 2,000 of them in the Milky Way. The fastest known pulsar rotates over 700 times per second. Elements heavier than helium, including the carbon in our bodies, the oxygen we breathe, and the iron in our blood, are created inside stars through nuclear fusion. When massive stars explode as supernovae, these elements are scattered into space, mixing with clouds of hydrogen gas and becoming incorporated into the next generation of stars and planets. Every atom of heavy elements on Earth and in our own bodies was forged in the nuclear furnace of a long dead star. The Milky Way has experienced billions of supernova explosions over its lifetime, progressively enriching the interstellar medium with these elements. Younger stars, including our Sun, contain a higher proportion of heavy elements than ancient stars. A chemical history written in starlight that reveals the galaxy's evolution. On average, the Milky Way experiences approximately 1 to 3 supernova explosions per century. However, because of obscuring dust, we don't see most of these events directly. The last supernova visible to the naked eye in our galaxy occurred in 1604, observed by Johannes Kepler, and now known as Kepler's supernova. Before that, Tycho Brahe observed a supernova in 1572. These spectacular events briefly outshine all the other stars in the galaxy combined, releasing as much energy in a few months as the Sun will emit over its entire 10 billion year lifetime. Despite their rarity from our perspective, supernovae play a crucial role in the galaxy's ecology, dispersing heavy elements, triggering new star formation by compressing nearby gas clouds, and creating neutron stars and black holes. Stars don't just shine passively. They blow powerful winds of charged particles into space, with the strongest winds coming from the most massive and luminous stars. These stellar winds collide with the surrounding interstellar medium, creating bubbles of hot, low-density gas that can span hundreds of light years. When massive stars explode as supernovae, they inject even more energy into these cavities, sometimes creating superbubbles that extend for thousands of light years. Our own solar system sits inside a region of lower density gas called the local bubble, a cavity roughly 300 light-years across, created by supernova explosions over the past 10 to 20 million years. This constant churning and recycling of gas helps regulate star formation throughout the galaxy. As the solar system orbits the galaxy, it also moves up and down relative to the galactic plane, completing one full oscillation approximately every 64 million years. Currently, we are about 95 light-years above the midplane and moving upward. At the peaks and troughs of this oscillation, when we're farthest from the plane, the solar system passes through regions with lower densities of stars and gas. Some scientists have speculated that these passages might correlate with mass extinction events on Earth, perhaps through increased exposure to cosmic rays or disturbances of the Oort cloud leading to comet showers. However, the evidence for such correlations remains highly controversial, and most astronomers consider these effects too weak to significantly impact Earth's biosphere. High-energy particles called cosmic rays constantly stream through the galaxy, accelerated to nearly the speed of light by supernova shockwaves and other violent processes. These particles, primarily protons and atomic nuclei, carry tremendous energy and can damage living cells. Earth's magnetic field and atmosphere shield us from most cosmic rays, but astronauts in space face increased exposure. The Milky Way's magnetic field, though incredibly weak by terrestrial standards, plays a role in guiding cosmic rays' paths through the galaxy. Understanding cosmic rays is important not only for space exploration, but also for comprehending the galaxy's energy budget and the processes that accelerate particles to such extreme velocities. Cosmic rays also contribute to the ionization of interstellar gas, affecting its chemistry and thermal properties. Threaded throughout the Milky Way is a weak but extensive magnetic field, approximately 1,000,000 times weaker than Earth's field, but spanning the entire galactic disk. This field is generated by the motion of ionized gas and the galaxy's differential rotation, acting like a cosmic dynamo. The magnetic field influences many galactic phenomena, from the propagation of cosmic rays to the formation of stars in molecular clouds. It also becomes visible in certain contexts, such as when astronomers observe the polarization of starlight caused by aligned dust grains. The field follows the spiral arm structure to some extent, though its detailed configuration remains a subject of active research. Understanding the galactic magnetic field helps explain how the Milky Way maintains its organized structure despite the chaotic forces acting within it. While globular clusters remain bound for billions of years, open clusters containing young stars have more temporary existence. These looser associations of hundreds or thousands of stars slowly dissipate as member stars drift apart due to gravitational interactions with passing gas clouds and other stars. Most open clusters dissolve within a few 100 million years, their former members scattered across the galaxy. The Sun likely formed in such a cluster 4.6 billion years ago, but its siblings have long since dispersed and are now impossible to identify with certainty. However, astronomers have recently begun using precise motion and composition measurements, from the Gaia spacecraft, to identify possible solar siblings, stars that formed from the same molecular cloud and still retain similar chemical signatures despite billions of years of separation. Unlike a solid body, the Milky Way doesn't rotate as a single unit. Stars and gas at different distances from the center orbit at different speeds. A phenomenon called differential rotation. This behavior arises because the galaxy's gravitational force weakens with distance from the center, similar to how outer planets orbit the Sun more slowly than inner ones. However, the rotation curve of the Milky Way, a plot of orbital velocity versus distance, doesn't decrease at large radii as it would if only visible matter contributed to the gravity. Instead, the curve remains roughly flat, providing crucial evidence for the existence of dark matter. The dark matter halo extends far beyond the visible disk, contributing additional gravity that keeps outer stars moving faster than they otherwise would. When astronomers first measured the velocities of stars and gas clouds at various distances from the galactic center, they expected to find that objects farther out moved more slowly, following the same pattern as planets orbiting the Sun. Instead, they discovered that the rotation curve remained essentially flat, with outer regions moving just as fast as regions closer in. This observation could only be explained if the galaxy contained much more mass than we can see, distributed in a vast halo extending well beyond the visible disk. This was one of the earliest and most compelling pieces of evidence for dark matter. Today, the study of galactic rotation curves continues to provide insights into the distribution and properties of dark matter, helping to constrain theories about its fundamental nature. One of the fundamental challenges in studying the Milky Way is determining accurate distances to objects within it. For nearby stars, astronomers use parallax, measuring the apparent shift in a star's position as Earth orbits the Sun. However, this method becomes increasingly inaccurate for distant objects. For more remote regions, astronomers rely on standard candles, objects with known intrinsic brightness. By comparing an object's true luminosity with its apparent brightness, they can calculate its distance. Cepheid variable stars, whose pulsation periods correlate with their luminosities, serve as excellent distance indicators. The Gaia spacecraft has revolutionized distance measurements by providing precise parallaxes for over 1 billion stars, creating an unprecedented three-dimensional map of the galaxy and revealing its structure with remarkable clarity. The bar of stars at the Milky Way's center plays an important dynamical role, channeling gas from the outer regions toward the nucleus. As gas clouds orbit through the bar region, gravitational forces deflect their paths, causing them to lose angular momentum and spiral inward. This process can fuel star formation in the inner galaxy and potentially feed the central black hole. The bar also affects stellar orbits, creating families of orbits with particular shapes and orientations. Stars on these bar-supporting orbits maintain the bar's structure against the galaxy's differential rotation, which would otherwise wind it up and dissolve it. The bar's strength and extent have likely varied over the galaxy's history, influencing the pace of its evolution. The Sun and nearby stars reside in a cavity called the local bubble, a region roughly 300 light-years across, where the density of gas is several times lower than average. This bubble was created by supernova explosions from a moving group of massive stars that formed nearby about 10 to 20 million years ago. As these stars evolved rapidly and exploded, their combined energy excavated a cavity in the interstellar medium, sweeping gas and dust away to create the relatively empty region we now inhabit. The walls of the local bubble glow faintly in X-rays from hot gas. A new star formation occurs where dense clouds encounter the bubble's edge. Living inside this cavity may have influenced Earth's climate and biosphere, though the precise effects remain uncertain. Within a few thousand light-years of the Sun lies the Gould Belt, a ring of young stars and star-forming regions tilted at about 20 degrees to the galactic plane. This structure includes many familiar stellar nurseries, such as the Orion Nebula, the Ophiuchus Molecular Cloud Complex, and the Taurus Dark Clouds. The Gould Belt may have formed when a dwarf galaxy or massive gas cloud passed through the galactic disk about 30 million years ago, triggering a wave of star formation that spread outward like a ripple. The presence of these nearby stellar birth sites has provided astronomers with unprecedented opportunities to study the star formation process in detail, revealing how molecular clouds fragment and collapse to create new solar systems. Some stars move through the Milky Way at tremendous speeds, much faster than typical stellar velocities. These hypervelocity stars can reach speeds exceeding 300 miles per second, fast enough to escape the galaxy's gravitational pull entirely. Several mechanisms can produce such high velocities. A binary star system might be disrupted by a close encounter with a supermassive black hole, with one star captured while the other is flung away at high speed. Alternatively, the supernova explosion of one star in a binary system can give the companion a gravitational kick. Some hypervelocity stars may be refugees from the Large Magellanic Cloud or other satellite galaxies, accelerated during their disruption by tidal forces. Studying these stellar speedsters provides insights into the galaxy's gravitational potential and the violent processes that can accelerate stars. Throughout the Milky Way exist objects called brown dwarfs, bodies too massive to be planets, but not massive enough to sustain hydrogen fusion and shine as true stars. With masses between about 13 and 80 times that of Jupiter, brown dwarfs generate heat from gravitational contraction and can briefly fuse deuterium, but they gradually cool and fade over time. These failed stars are difficult to detect because of their extreme faintness, and astronomers continue to discover them using infrared surveys. The nearest brown dwarf to Earth, Lumen 16, lies just 6.5 light-years away, closer than many stars. Understanding the population of brown dwarfs helps constrain theories of star formation and provides insights into objects that represent a transition between stellar and planetary physics. Not all planets orbit stars. Some wander alone through the galaxy as rogue planets, either ejected from their birth systems through gravitational interactions or formed in isolation from collapsing gas clouds. These unbound worlds travel through the darkness of interstellar space, their surfaces frozen and barren without a sun to warm them. Detecting rogue planets is extremely difficult because they emit very little light, but gravitational microlensing events occasionally reveal them when they pass in front of distant stars. Some estimates suggest rogue planets may be quite numerous in the galaxy, potentially numbering in the billions or more, though the true population remains highly uncertain. If a planet retained geothermal heat from its interior, it's conceivable that life which formed before its ejection might survive, though this remains purely speculative. When astronomers combine data from planet hunting missions like Kepler with statistical analysis, estimates suggest that the Milky Way may harbor tens of billions of Earth-sized planets orbiting in the habitable zones of their stars, regions where temperatures might allow liquid water to exist on planetary surfaces. Some studies have proposed numbers as high as 40 billion, though such figures remain highly uncertain. If we include potentially habitable moons around gas giant planets, the number could be even larger. This doesn't mean these worlds actually harbor life, only that they might have suitable conditions. The question of whether we are alone in the galaxy remains one of humanity's most profound uncertainties. The search for extraterrestrial intelligence continues through various programs, listening for radio signals or other signs of technology, but so far we have found only silence. The vast distances between stars make interstellar communication or travel extraordinarily challenging. The most ancient stars in the Milky Way, formed when the galaxy was young, consist almost entirely of hydrogen and helium, the primordial elements created in the Big Bang. These metal-poor stars contain only trace amounts of heavier elements, sometimes less than 1/10,000th the proportion found in the Sun. By studying these stellar fossils, astronomers can probe conditions in the early galaxy and learn about the first generations of stars that enriched the interstellar medium. Some extremely metal-poor stars may be second-generation objects, formed from gas clouds polluted by just a single supernova from a first-generation star. The search for such objects continues, as they provide unique insights into the chemical evolution of the universe. Contrary to earlier beliefs that all stars in a globular cluster formed simultaneously from the same gas cloud, recent observations reveal that some clusters contain multiple populations of stars with different chemical compositions. These distinct populations may have formed in several episodes, perhaps hundreds of millions of years apart. One possible explanation involves a scenario where the first generation of stars enriched the cluster's remaining gas through stellar winds, and this modified material then gave birth to second-generation stars. The presence of multiple populations complicates our understanding of globular cluster formation and evolution, suggesting these systems have more complex histories than previously thought. At the Sun's location, the thin disk of the galaxy measures only about 1,000 light-years thick, yet it extends roughly 100,000 light-years across. This makes it extraordinarily flat, like a compact disk, but even more so. If you scaled the galactic disk down to the size of a typical dinner plate, it would be thinner than a sheet of paper. This flatness results from the conservation of angular momentum. As the galaxy formed, the collapsing gas cloud flattened into a disk because rotation prevented complete collapse in the plane perpendicular to the spin axis, while gravity pulled material together along that axis. The resulting structure represents a balance between rotational and gravitational forces. Despite the Milky Way containing hundreds of billions of potentially interesting destinations, the distances involved make interstellar travel extraordinarily difficult with present or foreseeable technology. The nearest star system, Alpha Centauri, lies over 4 light-years away. Using conventional rockets, the journey would take tens of thousands of years. Even traveling at 1% of light speed, an ambitious target for advanced propulsion systems, the trip would require more than 400 years. Various concepts for interstellar spacecraft exist, including solar sails pushed by lasers, fusion rockets, and generation ships designed to support multiple generations during the journey. But none have moved beyond theoretical studies. For now, we explore the galaxy through telescopes, spectroscopy, and robotic spacecraft, while interstellar travel remains the realm of science fiction. Given the galaxy's age and the billions of potentially habitable planets it contains, some scientists wonder why we haven't detected any signs of extraterrestrial intelligence. This puzzle, known as the Fermi paradox after physicist Enrico Fermi, has spawned numerous explanations. Perhaps technological civilizations are extremely rare, or they tend to destroy themselves soon after developing advanced technology. Maybe intelligent life is common, but interstellar communication proves impractical across such distances. Or possibly, civilizations deliberately avoid contact, creating a cosmic zoo where Earth is observed but not contacted. Some solutions to the paradox are sobering, while others offer hope. The question remains open, and every new planetary system discovered adds urgency to our search for life beyond Earth. In the direction of the galactic center, and along much of the galactic plane, thick dust clouds create what astronomers call the zone of avoidance. This region, obscured by absorbing material, prevents us from seeing distant galaxies and even parts of our own galaxy in visible light. The zone of avoidance hampered astronomical surveys for decades, creating a blind spot in our view of the universe. However, observations at longer wavelengths, particularly infrared and radio, can penetrate this dusty veil. Modern all-sky surveys at these wavelengths have revealed thousands of galaxies hiding behind the zone of avoidance, including several relatively nearby galaxy clusters that were previously unknown. Within our own galaxy, the zone of avoidance conceals the central regions and portions of the far side of the disk. Just as archaeologists piece together human history from ancient artifacts, astronomers practice stellar archaeology, using the properties of old stars to reconstruct the Milky Way's formation and evolution. Each star preserves a record of the gas cloud from which it formed, encoding information about the galaxy's chemical state at that epoch. By measuring the abundances of various elements in stars of different ages, astronomers can trace how the interstellar medium has been enriched over time. Kinematic studies, examining how different stellar populations move through the galaxy, reveal past merger events and the gradual settling of the galaxy from a chaotic early state to its current organized structure. The fossil record written in starlight extends billions of years into the past, providing a historical archive of our cosmic home. Just as individual planetary systems have habitable zones where conditions suit liquid water and potentially life, the galaxy as a whole may have a habitable zone. Too close to the galactic center, intense radiation and frequent supernova explosions might sterilize planets or prevent life from arising. Too far out, the scarcity of heavy elements could make rocky planets rare. Our location in the galactic suburbs, at about 2/3 of the way from center to edge, may represent a sweet spot where conditions favor stable planetary systems and complex chemistry. However, this concept remains speculative, and life might prove more resilient than we imagine, thriving in environments we consider hostile. The search for life elsewhere in the galaxy will help determine whether such a habitable zone exists. Billions of years from now, the Milky Way will look very different from today. The collision with Andromeda will transform both galaxies into a single elliptical system. Star formation will eventually cease as the galaxy exhausts its gas supply, leaving only slowly aging stars. The most massive stars that exist today will have long since exploded as supernovae, while medium-sized stars like the Sun will have swelled into red giants and then collapsed into white dwarfs. In the far future, trillions of years hence, even these white dwarfs will cool to black dwarfs, dark cinders invisible in the void. The universe itself will continue expanding, perhaps accelerating ever faster, isolating merged galaxy clusters like islands in an increasingly empty cosmos. But these futures lie so distant that they remain almost unimaginable from our present perspective. Every element in our bodies except hydrogen originated in the nuclear furnaces of stars, or in the explosive deaths of massive stars. The calcium in our bones, the iron in our blood, the carbon forming the backbone of organic molecules, all were forged inside stars billions of years ago and scattered into space when those stars died. We are literally made of recycled stardust, participants in the grand cycle of matter that has repeated countless times throughout the galaxy's history. This connection between the human body and the cosmic realm represents one of astronomy's most profound insights. We are not separate from the universe, but an intimate part of it. Temporary patterns assembled from primordial hydrogen and stellar ash, briefly self-aware before dissolving back into the cosmic cycle from which we emerged. Observe the Milky Way at different wavelengths of light, and remarkably different views emerge. In visible light, we see the familiar band of starlight crossed by dark dust lanes. Infrared observations penetrate the dust, revealing the central bulge and spiral arms in detail. Radio wavelengths trace cold hydrogen gas and reveal the galaxy's large-scale structure. X-ray images highlight hot gas, supernova remnants, and the region around the central black hole. Gamma-ray observations show where cosmic rays interact with interstellar gas. Each wavelength provides unique information, and only by combining them all can astronomers construct a complete picture of our galaxy. This multi-wavelength approach represents one of modern astronomy's most powerful techniques. The European Space Agency's Gaia spacecraft is conducting the most precise survey of the Milky Way ever attempted, measuring the positions, distances, and motions of over 1 billion stars. This flood of data is transforming our understanding of galactic structure and dynamics. Gaia has revealed previously unknown stellar streams from disrupted dwarf galaxies, discovered thousands of new stellar clusters, and precisely mapped the three-dimensional positions of stars throughout our cosmic neighborhood. The spacecraft measures parallaxes accurate to within micro-arc seconds, allowing distance determinations for stars thousands of light years away. Gaia's data releases have sparked thousands of scientific papers and will continue influencing astronomy for decades to come. making this mission one of the most successful in astronomical history. One of the largest mergers in the Milky Way's past occurred roughly 10 billion years ago, when our galaxy collided with and absorbed a smaller galaxy now called Gaia Enceladus, named after both the Gaia spacecraft that detected it and the giant from Greek mythology. This ancient collision scattered stars throughout the inner halo and may have helped thicken the galactic disk. Evidence for this merger comes from the motions and chemical compositions of stars, which form a distinct population unlike other galactic components. Understanding past mergers like this one helps astronomers reconstruct the galaxy's assembly history and test theories of how large galaxies grow through the accretion of smaller systems. The Milky Way's current structure reflects this violent past, each component telling part of the story of collisions and growth. When giant molecular clouds collapse to form stars, they typically produce not individual stars but entire clusters containing hundreds or thousands of members. These young clusters remain gravitationally bound for at least a while, with the stars sharing a common motion through space. Some of the most spectacular celestial sights visible through telescopes are young star clusters, where hot blue stars illuminate surrounding nebulae of leftover gas and dust. The Pleiades, visible to the naked eye in the constellation Taurus, exemplifies this phenomenon. This beautiful cluster contains several hundred stars, born together roughly 100 million years ago, still drifting through space as a coherent group. Over time, gravitational interactions and encounters with other objects will gradually disperse these stars. But for now, they remain recognizable as a family. At the Sun's distance from the galactic center, stars and gas orbit at approximately 500,000 miles per hour. This tremendous velocity seems incomprehensible in human terms, yet it's just sufficient to balance the inward gravitational pull of the galaxy's mass. If we moved any slower, we would spiral inward toward the center. If faster, we would drift outward from our current orbit. This delicate balance has been maintained throughout the solar system's existence, allowing the Sun to complete roughly 20 circuits around the galaxy since its formation. During those orbits, the Sun has witnessed the galaxy's slow evolution, passed through spiral arms, and journeyed through varying environments while maintaining its stable place in the cosmic order. While most stars orbit the galaxy in the same direction, following the disk's rotation, some travel on retrograde orbits, circling in the opposite direction. These backward-moving stars are typically members of the stellar halo or belong to globular clusters. Their unusual orbits suggest they may have originated in satellite galaxies that were captured and disrupted by the Milky Way. When a small galaxy merges with a larger one, its stars retain their original orbital motions, which may be misaligned or opposite to the main galaxy's rotation. By studying the population of stars with retrograde orbits, astronomers can learn about the Milky Way's merger history and identify which stars are immigrants from other galaxies rather than natives of our own. As mentioned earlier, the solar system oscillates above and below the galactic mid-plane during its orbit, passing through the plane roughly once every 30 million years. During these passages, the solar system encounters higher densities of gas and dust, and the gravitational influence of material in the disk becomes stronger. Some researchers have proposed connections between these plane crossings and periodic phenomena on Earth, including climate changes or extinction events, though such correlations remain controversial. The periodic nature of our orbit provides a natural timescale for thinking about the galaxy's influence on the solar system, though most astronomers believe local factors dominate Earth's history more than galactic position. Some of the most striking features visible in images of the Milky Way are dark patches where few or no stars can be seen. These dark nebulae consist of dense clouds of dust and gas that block the light from stars behind them, creating silhouettes against the background star field. The famous Horsehead Nebula in Orion and the Coalsack Nebula visible from the southern hemisphere exemplify this phenomenon. Far from being empty regions, dark nebulae often harbor active star formation hidden within their dusty interiors. Infrared observations can peer through the obscuring material to reveal the newborn stars within. These dark clouds represent the raw material from which future generations of stars will form, cold reservoirs of gas waiting to collapse under gravity's patient pull. The galaxy doesn't exist in isolation, but remains connected to the surrounding intergalactic medium. Gas clouds fall into the Milky Way from its surroundings, providing fresh fuel for star formation. Some of this material comes from satellite galaxies being tidally stripped, while other gas may be primordial material left over from the galaxy's formation that is now falling inward. High-velocity clouds, clumps of gas moving at unusual velocities, rain down on the galactic disk from above and below, their origins still debated. This continued accretion helps explain how the Milky Way maintains star formation, despite billions of years of converting gas into stars. Without this replenishment, the galaxy would have long ago exhausted its gas supply and become a sterile collection of aging stars. With each generation of stars, the galaxy becomes slightly more metal-rich, meaning it contains a higher proportion of elements heavier than hydrogen and helium. The oldest stars are metal-poor, containing only trace amounts of heavy elements. Middle-aged stars like the Sun have intermediate metallicity. The youngest stars forming today have the highest metal content, benefiting from billions of years of enrichment. This chemical evolution provides a kind of clock, allowing astronomers to estimate stellar ages from their compositions. It also has profound implications for planet formation and life, as the abundance of heavy elements determines whether rocky planets can form and whether the complex chemistry necessary for biology is possible. Between stellar mass black holes and supermassive black holes may exist an intermediate category with masses ranging from hundreds to hundreds of thousands of solar masses. These intermediate mass black holes remain elusive, with only a few candidates identified. But astronomers theorize they might form in dense star clusters or through the merger of smaller black holes. Some globular clusters may harbor intermediate mass black holes at their centers, though detecting them proves challenging. Understanding this intermediate category could be important for explaining how supermassive black holes grew to their enormous sizes. One possibility is that they grew from intermediate mass seeds that formed in the early universe, gradually accreting mass over billions of years. though this remains an area of active research. Rather than thinking of the galaxy's history in terms of billions of years, we might use the galactic year, the time it takes the Sun to complete one orbit around the galaxy. Since one orbit takes roughly 230 million years, the Sun has completed only about 20 galactic years since its formation. Life appeared on Earth roughly 15 galactic years ago. Dinosaurs arose about 1 galactic year ago and went extinct just a third of a galactic year before the present. This cosmic calendar compresses astronomical timescales into more comprehensible units, though it still challenges our intuition. On the timescale of galactic years, human civilization has existed for only the briefest moment, barely a cosmic instant. The fact that ancient globular clusters still exist tells us something important about the galaxy's history. These systems are tightly bound by gravity, making them resilient to disruption. During the Milky Way's formation, when mergers and close encounters were common, many looser stellar associations must have been torn apart, their stars scattered. The globular clusters survived because their compact structure and deep gravitational potential wells protected them from destruction. They are cosmic survivors, preserving information about conditions in the early galaxy within their ancient stellar populations. Each cluster represents a time capsule from an epoch billions of years in the past. Beyond the local group lies the Virgo supercluster, a massive collection of galaxy groups and clusters spanning roughly 100 million light-years. The Milky Way and Andromeda, along with the rest of the local group, occupy the outskirts of this structure. But even the Virgo supercluster is just one component of an even larger structure called Laniakea, a basin of attraction containing 100,000 galaxies. These nested structures reveal that the universe is organized hierarchically, with galaxies grouped into clusters, clusters into superclusters, and superclusters into the largest structures known. The Milky Way's motion through space reflects the gravitational pull of these enormous assemblages of matter. The Milky Way's form is not static, but constantly being reshaped by gravitational forces. Interactions with satellite galaxies create tidal tails and stellar streams. The passage of spiral density waves triggers star formation in molecular clouds. The bar channels gas toward the center. Even the gravitational influence of individual molecular clouds can deflect stars from their orbits slightly, a process called dynamical friction that gradually transfers energy and angular momentum. These countless gravitational interactions, acting over billions of years, have sculpted the galaxy into its current form and will continue shaping it in the future. The galaxy is a dynamic system in constant motion and evolution. From Earth, we can observe perhaps 1% of the Milky Way directly at visible wavelengths. The rest is hidden by dust or lies beyond the limits of our telescopes. Even within our local neighborhood, thousands of light years in all directions, many faint stars and brown dwarfs remain undiscovered. The far side of the galaxy, tens of thousands of light years beyond the galactic center, is almost completely unknown at optical wavelengths. Only by using infrared and radio observations can astronomers map the galaxy's full extent and structure. This limited perspective means that many discoveries about the Milky Way's nature are relatively recent, and many more likely await future observations as technology continues improving. Measuring the distances to nearby stars was one of astronomy's great challenges. Finally achieved in 1838, when Friedrich Bessel measured the parallax of the star 61 Cygni. Parallax is the apparent shift in a star's position as Earth orbits the Sun, with closer stars shifting more than distant ones. The method works like depth perception in human vision, using the baseline between two observation points to determine distance through geometry. However, stellar parallaxes are extremely small, measured in fractions of an arc-second, which is why accurate measurements required telescopes and precise position measurements. Today, the Gaia spacecraft has measured parallaxes for over 1 billion stars, revolutionizing our three-dimensional understanding of the Milky Way's structure. Ancient cultures around the world noticed the luminous band crossing the night sky and gave it various names, many referring to milk or pathways. In Greek mythology, it was spilled milk from the goddess Hera. The term Milky Way comes from the Latin Via Lactea, meaning Milky Road or Milky Way. Not until Galileo pointed his telescope at this band in 1610 did anyone realize it consisted of countless individual stars, too faint and close together to distinguish with the naked eye. What appears as a milky glow is actually the combined light of billions of distant suns, viewed edge-on from our position within the galactic disk. The name persists, though we now understand its true nature as our cosmic home. Throughout the Milky Way shine red giant stars, bloated and luminous, their surfaces cooled to ruddy hues. These stars have exhausted the hydrogen in their cores and begun burning helium or are transitioning between fusion stages. As a star evolves off the main sequence, it swells enormously, with some red giants growing large enough to encompass Earth's orbit if placed at the Sun's position. Current stellar models suggest that in about 5 billion years, our Sun will become a red giant, potentially expanding to perhaps the orbit of Mars and possibly engulfing the inner planets. Red giants eventually shed their outer layers, creating beautiful planetary nebulae and leaving behind white dwarf cores. These dying stars return material to the interstellar medium, contributing to the cycle of stellar birth and death that enriches the galaxy. For stars like the Sun, the ultimate fate is to become a white dwarf, a dense stellar remnant roughly Earth-sized, but with a mass comparable to the Sun's. Supported against further collapse by electron degeneracy pressure, a quantum mechanical effect, white dwarfs slowly cool over billions of years, gradually fading from white-hot to red to eventually black. The galaxy contains billions of these stellar corpses, most too faint to detect individually. In globular clusters, the oldest white dwarfs have been cooling since near the dawn of the universe, and their temperatures provide independent age estimates for these ancient systems. Eventually, in a timeline exceeding the current age of the universe, white dwarfs will cool completely, becoming theoretical black dwarfs, though none yet exist. When sun-like stars shed their outer layers near the end of their lives, they create planetary nebulae, glowing shells of gas illuminated by the hot white dwarf core. Despite their name, planetary nebulae have nothing to do with planets. Early astronomers using small telescopes thought they resembled planetary disks. These nebulae exhibit intricate structures, from simple shells to complex bipolar outflows and irregular filaments. They last only about 10,000 years before dispersing into the interstellar medium, making them cosmically ephemeral. The Milky Way contains thousands of known planetary nebulae, each representing a star's transition from red giant to white dwarf. Their study helps astronomers understand stellar evolution and the return of processed material to the galaxy. Despite decades of study, determining the Milky Way's total mass proves surprisingly difficult. Estimates range from about 800 billion to 1.5 trillion solar masses, with much of the uncertainty arising from the dark matter halo's extent and density profile. Different measurement techniques yield different results, depending on whether astronomers use stellar velocities, satellite galaxy motions, or the distribution of globular clusters. The mass determines many important properties, including the galaxy's future and its interactions with other local group members. As measurements improve, particularly from the Gaia mission and studies of distant satellites, astronomers are gradually converging on a more precise value, though significant uncertainty remains. The Milky Way formed stars much more rapidly in its early history than it does today. At its peak, several billion years ago, the galaxy may have produced tens of solar masses worth of new stars per year. Today, that rate has dropped to roughly 1 to 3 solar masses annually. This decline reflects the gradual consumption of gas through star formation and the expulsion of gas by stellar winds and supernovae. Eventually, star formation will cease entirely as the galaxy exhausts its gas supply, though continued accretion from satellite galaxies and the intergalactic medium may prolong the process. The merger with Andromeda will trigger a brief surge in star formation as gas clouds collide, but afterward, the combined galaxy will gradually fall silent. The major spiral arms of the Milky Way are not identical, but have distinct properties. The Perseus arm, farther from the galactic center than the Sun, contains many bright star clusters and nebulae. The Scutum Centaurus arm, on the opposite side of the galaxy, represents one of the two major structures emerging from the central bar. The Sagittarius arm, lying between the Sun and the galactic center, is less prominent. These arms don't represent permanent structures, but rather waves of enhanced density moving through the disk. As gas clouds enter an arm, they compress, triggering star formation. The newly formed massive stars illuminate the arm with their intense light, making the spiral structure visible. These stars live only a few million years, meaning they die before leaving the arm, which helps explain why the arms remain distinct. Given enough time, all the galaxies in the local group may eventually merge into a single massive system. The Milky Way-Andromeda collision, if it occurs, will be the first and largest merger. But smaller galaxies like Triangulum and various dwarfs will likely be incorporated as well over time. This process would take many billions of years, far longer than the current age of the universe. Based on current understanding of galactic dynamics, the final product could be a giant elliptical galaxy containing all the stars and gas from its constituent members. By that distant epoch, most star formation will have ceased, leaving a slowly aging population of red stars gradually fading over trillions of years. This represents the potential ultimate fate of our cosmic neighborhood in the standard cosmological model, assuming dark energy doesn't tear everything apart first. When a massive object passes in front of a distant star, its gravity acts like a lens, briefly magnifying the background star's light. This gravitational microlensing provides a way to detect otherwise invisible objects like brown dwarfs, rogue planets, and black holes. Surveys monitoring millions of stars in dense fields toward the galactic center or Magellanic Clouds have detected thousands of these events. Each reveals information about the lensing object's mass and distance. Microlensing has discovered numerous exoplanets and even provided evidence for a population of planet-mass objects drifting freely through the galaxy. This technique will continue revealing hidden components of the Milky Way that emit little or no light. By measuring the abundances of various elements in stars of different ages, astronomers can reconstruct the galaxy's chemical history. The oldest stars contain almost exclusively hydrogen and helium from the Big Bang. Subsequent generations show progressively higher abundances of heavy elements, tracking the cumulative output of billions of supernovae over cosmic time. Different elements trace different nucleosynthetic processes. Oxygen and silicon come primarily from massive star supernovae. Iron peaks in Type Ia supernovae from white dwarf explosions. Elements heavier than iron are mostly created in neutron star mergers. This chemical archaeology reveals not just when stars formed, but also the diversity of processes that have enriched the galaxy's composition over 13 billion years. Some of the most spectacular discoveries from the Gaia spacecraft are stellar streams, long filaments of stars stretched around the Milky Way by tidal forces. These streams mark the remains of globular clusters or dwarf galaxies torn apart during close encounters with our galaxy. By mapping their positions and velocities, astronomers can reconstruct the orbits of the progenitor objects and constrain the distribution of dark matter in the galactic halo. Some streams wind multiple times around the galaxy, like ribbons wrapped around a ball. Others extend in relatively straight lines, marking recent disruptions. Each stream tells the story of a cosmic collision, a smaller system sacrificed to build the Milky Way we see today. Despite the universe's expansion, the local group remains gravitationally bound, meaning its members won't be carried apart by cosmic expansion. This occurs because on small scales, gravity overcomes the expansion, holding together galaxies that are already close to each other. The local group's fate is therefore decoupled from the larger expansion. While distant galaxy clusters recede faster and faster, carried by accelerating expansion, The local group will contract and merge over billions of years. This represents a common pattern across the universe, with nearby objects remaining bound while more distant structures separate ever faster. The boundary between these regimes defines the cosmic horizon, beyond which expansion eventually overcomes all other forces. Future astronomers, billions of years from now, will see a very different Milky Way. Star formation will have ceased, the spiral arms will have dissolved, and the merger with Andromeda will have transformed the galaxy's structure. Many of the bright stars we see today will have long since exploded or faded. Conversely, observers in the distant past would have witnessed a more chaotic, rapidly evolving galaxy with higher star formation rates and perhaps more frequent mergers. We observe the Milky Way during a relatively stable period in its middle age, with well-defined structure and ongoing but moderate star formation. This represents neither the galaxy's youth nor its old age, but a mature phase that will last for several more billion years. Because we can study the Milky Way in far greater detail than any other galaxy, it serves as a Rosetta Stone for understanding spiral galaxies everywhere. Processes we observe in detail here, from star formation in molecular clouds, to the dynamics of spiral arms, to the behavior of dark matter halos, apply to galaxies throughout the universe. By understanding our own galaxy thoroughly, we gain insights that help interpret observations of distant galaxies seen only as faint smudges. Conversely, studying other galaxies from the outside provides perspectives impossible to achieve. From within the Milky Way, such as seeing the overall spiral structure clearly. The two approaches complement each other, advancing our understanding of how galaxies form, evolve, and behave. Modern astronomy has embraced citizen science, enlisting volunteers to help process vast amounts of data. Projects like Galaxy Zoo initially focused on classifying distant galaxies but have expanded to include studies of the Milky Way. Volunteers have discovered new stellar clusters, identified unusual variable stars, and even found previously unknown planetary nebulae. With modern surveys producing more data than professional astronomers can analyze alone, these contributions prove invaluable. The combination of human pattern recognition and computer algorithms working together achieves results neither could accomplish alone. As astronomy enters an era of massive data sets from projects like Gaia and upcoming telescopes, citizen science will play an increasingly important role in exploring the galaxy. Looking at the Milky Way stretching across a dark sky provides a visceral reminder of our place in the universe. We are not separate observers looking at distant objects, but participants embedded within a vast cosmic structure. Every visible star is our neighbor in space. Every nebula a region where new solar systems might be forming. The thin band of light represents our view into the depths of our own galaxy, looking through the disk from our position within it. This perspective simultaneously humbles and inspires, showing how small we are, yet also how we've come to understand these immense cosmic systems through observation and reasoning. The Milky Way is both our address and our destiny. Despite tremendous progress, many fundamental questions about the Milky Way remain unanswered. What exactly is dark matter? How many planets in the galaxy support life? What triggered the formation of the spiral arms? How will the merger with Andromeda precisely unfold? What is the complete history of the galaxy's assembly? Future observations will address some questions while undoubtedly raising new ones. Each answer opens doors to deeper understanding while revealing new layers of complexity. The study of the Milky Way represents an ongoing journey of discovery, with each generation of astronomers building on previous work while developing new techniques to probe the galaxy's secrets. It's remarkable that despite living within the Milky Way, we continue making fundamental discoveries about its structure. The realization that we live in a barred spiral came only in the past few decades. The detailed mapping of stellar streams began in earnest only in the 21st century. The precise measurement of the distance to the galactic center remains uncertain within about 10%. Even the number of spiral arms is debated, with some studies finding 2 major arms and others claiming 4. These ongoing discoveries reflect both the challenge of mapping a structure from within and the rapid advancement of observational capabilities. Future missions will undoubtedly reveal aspects of the galaxy we haven't yet imagined. Studying the Milky Way helps us understand our planet's place in the cosmos and the context for life's existence. The chemical elements in our bodies came from stellar nucleosynthesis. The Sun's orbit through the galaxy has exposed Earth to varying cosmic ray fluxes over millions of years. Some researchers have proposed that the solar system's location in what they call the galactic habitable zone may have been important for complex life to evolve, though this concept remains debated. Even the search for extraterrestrial intelligence requires understanding the distribution of stars and planets throughout the galaxy. We cannot fully comprehend Earth's story without considering the larger galactic environment in which it formed and evolved. The galaxy is not just our cosmic address, but an integral part of understanding terrestrial existence. Whatever the future holds for humanity, the Milky Way will continue its cosmic journey. Stars will be born and die. Gas will be recycled, and slow gravitational evolution will reshape its structure. If the collision with Andromeda occurs, it will transform both galaxies into something new. Eventually, trillions of years in the future, current cosmological models suggest the last stars will flicker out, potentially leaving a dark galaxy of stellar remnants orbiting through an ever more empty universe. But that future lies so distant as to be almost meaningless, and our understanding of such extreme timescales remains highly uncertain. For now, the Milky Way shines brightly above us, an island of light in the darkness, our home among the stars. And so we conclude our journey through 100 facts about the Milky Way galaxy. As we've drifted through this cosmic landscape, we've seen how our galaxy formed, evolved, and continues changing. We've explored its structure from the central black hole to the distant halo, from ancient globular clusters to stellar nurseries where new suns ignite. We've learned how we fit into this vast system, inhabitants of a small rocky world orbiting an ordinary star in the galactic suburbs, yet capable of comprehending the immense structure surrounding us. The Milky Way is not just a collection of stars, but a living, evolving system, a cosmic ecosystem where matter is continually recycled through stellar birth and death. It is our home, the place where everything we know exists, where every human drama has played out beneath its faint glow. When you look up at a dark sky and see that luminous band stretching overhead, you're seeing your own galaxy from within, looking into the depths of our cosmic dwelling place. Let these thoughts carry you into rest now. Close your eyes and imagine yourself drifting through that vast spiral, past glowing nebulae and ancient stars, through clouds of gas awaiting their transformation into new solar systems, across billions of years and hundreds of thousands of light years. The universe is vast and old, but we are part of it, made from the same materials that form stars and planets, connected to the cosmos through deep and ancient ties. Rest well, knowing that above us the Milky Way continues its eternal dance through space, slowly turning, gradually evolving, a river of light flowing through the darkness, carrying us all on a journey that began billions of years ago and will continue for billions more. The galaxy watches over us, as it has since the first humans looked up in wonder, and it will continue long after we are gone, eternal and magnificent, our home among the stars. If you enjoyed this exploration, feel free to like, subscribe, and leave a comment below. Your support helps me create more content like this. But for now, simply rest. Let the gentle motion of the Milky Way through space carry you into peaceful sleep. Good night.